Hi, this is Yao from VANTAGE TUTOR, a class above the rest. Now, today we're going to try another question. This is on reaction kinetics, and this is from Hwa Chong Institution 2016, paper 3, question 1C. Okay, so if you want to have a look at this question, want to try it on your own, pause this video right now, try this question right now. If not, you can go online and look for the soft copy. We're going to get started in about 5 seconds. Right, so this question is your typical reaction kinetics question. Maybe not so typical. Let's see. Now, this is something that's very familiar to most students, where you have a table of volume of Fa1, Fa2 with a solvent, and they tell you the rate of the reaction that they get. Okay, then from there you're supposed to deduce the order of reaction. Okay, now most students, when they see this, in most A-level questions, you can usually just dive right into it. Why? Because essentially you're just doing proportion. When something times 2, what happens to the rate, then from there you can deduce the order of reaction. But most students tend to forget that you need to check for the total volume. Now if I look at the first column, you can see that the total volume is actually 100 cm cubed. Second one is only 50. Okay, and the last one is only 50 as well. And therefore, you cannot actually just jump into the comparison straight away. Now, to be fair, in your A-levels, this shouldn't happen, or rather in the real lab, this shouldn't happen, because most of the time we standardize the volume and we just go according to the question. Just go according to the experiment and we just start calculating. Okay, so I don't know why Hwa Chong came out with this question. Extra. But yeah, so I guess this is a good question for us to test ourselves with. Alright, so you can see the experiment 2 and 3. The volume is not consistent, so for me, I'm more of a multiply guy. I'm going to take the total volume of experiment 2 and times 2. Okay, so instead of saying 5, 20, 25, it will be 10, 40, and 50. And you can see that this should add up to become 100. Now, should the rate of reaction change? No, because everything in the mixture, Fa1, Fa2, and the volume of solvent all increase proportionately. So my rate of reaction don't change, but my total volume has changed. From here is something that you are very familiar with, which is essentially you can just do your comparison, right? So if I compare experiment 1 and 2, okay, I can say that you can see Fa1, okay, pardon me right there, Fa1, the volume is the same. However, Fa2, the volume has been divided by 3 times 4. Okay, so now let's go back. So by using experiment 1 and 2, comparing, okay, Fa2, I can see that in experiment 1, Fa1 in experiment 1 multiplied by 4 over 3. Okay, to become in your experiment 2. Okay, so now I can say that the concentration of Fa1, okay, has multiplied by 4 over 3, and then the rate, okay, if you take your GC, alright, so I'm expecting 7.4 divided by 3 times 4, okay, I get 9.86 times 10 to the power negative 7, so rate also times 4 out of 3. Okay, therefore, I can say that it is first order with respect to Fa1. Okay, and that's my first part. Very simple, done. Alright, now to find the order of reaction of the second solution, which is Fa2, this might seem like a problem, because right now if you look at it, Fa2, I just did Fa2, now we're doing Fa1. Okay, so if you look at Fa1, more or less almost the same. So now let's compare experiment 2 and 3, okay, using the total 50 cm cube. So experiment 2 and 3. Okay, let's compare experiment 2 and 3. So for the sake of completion, I'm going to show you the other way of doing your comparison. Instead of doing your proportion, I can actually do mathematical. Okay, so I can say that rate 2 over rate 3 equals to K order of reaction FA1 and FA2 over K order of reaction FA1 FA2, for which we know that your order of reaction for FA2 from what we found just now, was it FA2 that we found? Yeah, it's not FA1, FA2, my mistake. It's first order. So this first order and first order. So let me just make a change over here right now. Okay, so this is gonna be FA2. Okay, with respect to FA2. Okay, so now if I look at this equation, my K constant does not change because I hold it at the same temperature. I get cancelled out. Okay, then I can put in the rest of my values, where my FA1 has an unknown order of reaction, I call it N. Okay, so let's go back to my equation. I can see that in rate equation 2, so I just put in all the numbers, so it's 9.86 divided by 4.93 equals to FA1 in experiment 2 is 5 multiplied by 40. Okay, this power N. Okay, divided by 10 power N multiplied by, oh, see, I confused myself. It's not 40, it's 20, because I'm doing in terms of total 50. Okay, what I mean by that is this part, this 50. Okay, both are in terms of total 50. So let's go back. Okay, so this is gonna be 20 and this is gonna be 5. Okay, so from here just math. Okay, press my calculator. 9.86 divided by 4.93 times 5 divided by 20. This is half. So I can say that I continue move down. This is basically half equals to 5 over 10 power N. So I can say that therefore N equals to 1. And now I can conclude that it is first order with respect to FA1, whatever the molecule is. Okay, so if I'm not wrong, FA2 is your NaOH, FA1 is your organic compound, so you're expecting a SN2 reaction, which is your part 2 answer. Okay, so we're going to take a 5-second short break right now, then we're going to start with part 2. Alright, welcome back to part 2. So part 2, reference to your answer in C part 1, describe the mechanism. Alright, describe the mechanism. Okay, so whenever we talk about describing a mechanism, you have to draw your arrow pushing, your curly arrows, your dipole moment, whatever. So in this case, given that we already established that in part 1 that your rate equation is equals to K NaOH and your compound. So what's your compound again? 2-bromo 3-methyl butane. So 2-bromo 3-methyl butane, so 1, 2, 4, 2-bromo and 3-methyl. So you have a bromo over here, you have a methyl group over here. Okay, so you're expecting a reaction over here. Okay, now most students, whenever they draw SN2 reaction, they tend to forget their inversion of the umbrella and their 3D structure. So I'm going to show you right now how to do it. Okay, so let's go to my molecule. So very often I just focus on my carbon, where I have a Br. So my Br, let's just say that I go this way, this is my Br. And then I have one hydrogen and another R group. So one hydrogen, okay, R group over here. So this CH3. Okay, and the other one is basically carbon this way. Okay, so I'm gonna add my NaOH. So plus OH minus, okay, indicate my lone pair, indicate my dipole moment, indicate my arrow pushing. So this arrow is going to attack from the back side, okay, and this will leave. Okay, the next part is about drawing your intermediate. Some schools say that you don't need to draw it anymore, so I'm not going to say much about it. For me, I've been taught that I need to draw it. So for the ones leaving is BR, so this must be dotted. Okay, this is leaving. And then something coming in is your OH, so this is your intermediate state. And the rest you can just draw it flat. So CH3, okay, CH3. Then I have my H and I have my R group. Okay, so from here, draw my intermediate. Next part. Okay, you need to show me the inversion of the umbrella. So C, go to the other side. I have my, okay, I have my over here. CH3, H, then I have 1, 2, 3. Okay, and then I put in my R group, not my R group, but my OH group. And then I need to balance with my plus BR minus. Okay, so this is essentially a one-step reaction. There's no slow or fast. Alright, so let's take another 5-second break before we move on to part 3. This is your SN2 reaction. Alright, the very last part. You need to calculate the rate constant. Okay, stating the units. Okay, so how to calculate the rate constant? Alright, so let's take this down here. Rate constant very often is just your K. So to calculate a rate constant, you need to know the rate of reaction, your given concentration of each reactant, and then you just do some algebra manipulation, solve for a rate, and at the same time solve for your units. Okay, so I'm going to do it right now. So rate is equals to K, okay, NaOH, and then your organic compound. Just now I didn't draw it up here, so I should have. I forgot my square bracket to complete it. Okay, so this is gonna be 2 bromo. Okay, 2 bromo. What's that? 2 bromo 3 methyl butane. 3 methyl butane. Okay, so let's just pick one experiment. For me, I think I prefer experiment 1. Doesn't matter which one you pick, so it's just 7.4 times 10 to the power of -7 equals to K. And then now I'm doing my concentration. So as I know, my concentration is proportional to my volume. However, at the same time, my total volume needs to come into play, or my total volume of the mixture should come into play in terms of determining my final concentration. So this is going to be K. Okay, firstly, I can first find the mole of NaOH. So NaOH in my first case is just 10 divided by 1000 times 0.01. Okay, divided by my total volume, which is 100 divided by 1000. Okay, then for my 2 bromo 3 methyl butane, what a mouthful, is basically just taking your 30 divided by 1000 multiplied by 0.01 as well, divided by my total volume, which is 100 over 1000. Okay, so from here I just press my calculator. Okay, so you should get something like 10 divided by 1000 times 0.01 times 30 divided by 1000 times 0.01 divided by 100 divided by 1000 square. Okay, square. So this should give you 7.4 times 10 to the power -7 equals to K bracket 3 3 times 10 to the power negative 6. Okay, then going further, k is therefore equals to 7.4 times 10 to the power negative 7 divided by this, okay, is about 0.247. Okay, so I need to do my units, so I'm going to do my units on the right hand side. Okay, so my units, as I know my rate is supposed to be mole per dm cube per second, equals to my first order and first order, so the overall is second order, so it's basically mole per dm cube square, for which I can cancel out this, and therefore my k is very simply just mole negative 1 dm cube as power negative 1. Okay, so I just put in my units right now in red, so this is gonna be mole power negative 1 dm cube negative power 3 second. Okay, now I've completed this whole entire question. I don't know how long I took. I've given you plenty of breaks. So this is the first time I'm doing it on YouTube, because I realized my videos are a bit long for TikTok. So I hope you guys actually came here from TikTok to actually have a look at my videos, and more importantly, I hope my students learn something from this. Okay, always take note of the total volume. Okay, even though in reality, total volume for all our experiments should be constant. We don't do things like this. Okay, so I hope you learned something from this reaction kinetics. This is Yao Le from VANTAGE Tutor. Class above the rest.